Hello everybody, welcome to the course of Scaling or Scalable Data Science. Today's lecture is on Introduction to Hashing. My name is Anirban Dasgupta. I am a professor of Computer Science and Engineering at IIT Gandhinagar. So let's begin. The outline of today's lecture will involve looking at hash tables and hash functions. While this might be something that you have touched upon in your undergraduate algorithms class, we will go into it in a little more details. We will first see that what makes a good hash table, what makes a good hash function, right? And in order to define this well, we will introduce the concept of universal hashing. Okay? Then we will look at some analysis of a hash function or a hash table in terms of the query time, right, and the concept of chaining will come in here. We will then look at how to construct good hash tables, and in this lecture itself we will look at one very simple example of simple construction for a good hash function. So, here is the basic problem. Suppose you have a library, right, that has a huge number of books, and you have organized it in whatever manner you can. Now, somebody comes to you and gives you one particular book, and you have to ask the question of whether this book is present in your library or not. Okay. So, what is a naive algorithm for this? The most naive algorithm would be a linear search through your entire data set. Okay. We can always do that, but can we do better than this? Can we pre-process the data that we have to build a data structure, so that we are answering the query of that given any particular element, we are answering the query of whether it belongs to my data set in time that is much faster than going through the entire data set. And for this, we will construct a hash table. A hash table is at its heart a very simple data structure. We start by assuming that the elements come from a universe U, right. Think of this as, let us say, the titles of all the books or the ISBN numbers of all the books. But while the universe U is large, at any point we need to store only n items, small n items, and small n is potentially much less than the cardinality of the entire set U. Our hash table data structure will consist of two parts. One is a simple array of size m, right. So, the size that we choose m here, the size m that we choose here will be bounded by our access to memory. How much memory do we have? How big can we make the hash table? The next is the most important part of a hash table, a hash function, and this is a function that maps every element of U into a number from 0 to m minus 1. So, think of a hash function as telling you the following: given the element x, in which position of the array should you place the element x, right. So, h of x will give you the position of the array in which to place element x. Okay. Again, we will typically use m that is much smaller than the cardinality of the universe. M will also be much smaller than typically be much smaller than the size of the elements that you need to keep, right. And because of this, because m is less than n, collisions are bound to happen, right, by something, if you have read about it, called the pigeonhole principle. So, collisions, we call it a collision when for two elements x and y of the universe, x does not equal y, but h is asking them to map into the same position of the array. That is, h is telling you that h of x is equal to h of y, and so you should be putting both of these in the same position of the array, and we call this a collision. So, why do we look at collisions, right? In theory, what are we looking to do, right? What we are looking to do is keep all the elements x in the same position h of x, right. So, therefore, if there is collision, then in some sense the elements are lumping up at the same position at the same place in the hash table, right. So, what we want is to kind of distribute it distribute the elements of the universe as uniformly across the as uniformly across the array as possible, right. And it is clear that you cannot do this always. Suppose, so consider this, suppose you came up with a deterministic hash function, okay, and you showed this to your adversary, right. Now, by the pigeonhole principle, this deterministic hash function h that you have created maps a lot of elements into the same position, into one place of the hash table, right. Let us say position 0. So, your adversary could now give you a data set, right, that consists exactly of those elements of the universe, right. That is basically what it does, it takes h inverse of 0 and gives you that as a data set, right. So, then anything that you do has to boil down to just naive search over these elements, okay. So, in some sense we cannot really guarantee anything if you are choosing your hash function in a deterministic manner and if your adversary is powerful to sort of look at this hash function and design the data set. And therefore, what we resort to is what is known as a randomized algorithm. That is, what we say is that okay, the hash function will not be chosen deterministically, but it will be chosen randomly, presumably from a family of functions. Okay. So, the most ideal way to choose a hash function seems to be choosing a function at random, that is out of all possible functions. Okay. So, in that case the family H that we are talking about could potentially be the family of all the functions that go from u to m, right, that go from u to the set 0 to m minus 1. Okay. And at runtime, what the algorithm is going to do is that it is going to pick a single hash function out of this set, out of this family H. Okay. And what we will then do is analyze the expected query time of the algorithm. So, this expectation that we take here is really over the choice of the hash function. It is very important to remember that the algorithm's random choice, right, is the choice of the hash function, and the analysis of the algorithm happens with respect to this randomness. So, it might seem natural to choose the hash function uniformly at random out of all possible functions. However, there is a catch here, right, and this catch is as follows, that because the algorithm has to also carry around a description of the hash function, right, because remember, when the query comes, the algorithm again has to calculate the value of the h of the query, right. So, therefore, it has to carry around code that is essentially the description of the hash function with itself. So, therefore, in an information theoretic sense, if the size of the family is h, is cardinality of h, right, the algorithm has to carry logarithmic number of bits in the cardinality of h as the description of the hash function, right. And if the set h is the set of all the hash functions m to that maps u to the set m, right, then log of the cardinality of h is also large, right. The log of the cardinality of h is basically cardinality of u times log of m, right, which is fairly large, and we do not want to do that. So, therefore, what we will try to do is to try to create hash families that are small in size, right, and we will see, we will make this precise in a little more. So, what we need to create are small hash families such that choosing a function from it gives me a function with good behavior. So, what is this definition of behavior? The simplest notion of a function with good behavior is one that is uniform, right. That is, you could potentially say that the hash function, that given any x, the hash function maps it into a position I with probability 1 by m, right. That is the probability over all h belonging to h the event that h of x equals I equals 1 by m for all x and for all I. It turns out that this is not enough, right. This is not enough, because you could it's not very hard to construct hash families that really are constant, that are mapping all elements of the universe into only one position of the array and still satisfies this requirement. Okay. So, this is not enough. A slightly better definition is that of a universal hash function. What is universal? The definition of a universal hash function says that given any two elements x and y that are not equal to each other, okay, what is the chance that h maps both of them into the same position of the array? Okay. If you take a minute and think about it, if we were choosing h to be uniformly and random among all possible hash functions, this chance is exactly 1 by m. Okay. So, therefore, let us just take that value, right. What we are saying is that a hash family capital H is called universal if, when we choose a single hash function small h from this family capital H, the probability that h of x equals h of y equals 1 by m, and this happens for all pairs x and y. Okay. So, as of now it is not clear that there exists such a universal family, right, other than the Nye family of all possible functions, but we will soon see how to construct one such family. Okay. Sometimes what will happen is that we will not be able to construct families that are exactly universal, and then what we go for are near universal families. So, a near universal hash family is one where this equality, that this probability, the probability of collision, is at most, let us say 2 by m or some c by m, and we will call this a C near universal hash family. Okay. So, why are we looking at the definition of universality? So, we are looking at the definition of universality because of this particular construction. So, we have not really told you what happens when two elements x and y collide, right. For instance, look at this picture, that suppose this blue thing is the array that we are looking at, is the array of size m, and we have positions 2, 5 and 9. Now, in position 2 we have 3 elements of the universe that have mapped into position 2. Similarly, in position 9 there are 2 elements that have mapped. So, what do? It's very simple. What we do is that we basically keep all the IDs of all the elements that have mapped into the same position using a linked list that has a root at that position, right. So, because there are 3 elements that have mapped into position 2, we keep a linked list of size 3 and the root of the linked list is the position 2. Similarly, we keep a linked list of size 2 starting at the position 9. Now, what happens when I get an element, when I get a query? I map it into the corresponding position of the array using the function h, then I look at the linked list starting from that position. If there is no linked list there, then of course I say no, this particular query does not exist in the hash table, but if there is a linked list, then you go over all the elements of the linked list trying to find that element. Okay. So, how do we get the expected time for a query? The expected time, supposing L of x, so suppose the query is the element x, right. So denote by L of x the length of a chain starting at position hx. Therefore, the expected time to query the element x, to say yes or no whether this element x belongs to the hash table or not, is given by this expression. So, first you have to calculate the hash table, the value h of x for the element x, and that is going to take order 1 time, let us say, right. And after that you have to go over the entire linked list L of x trying to find this element x, right. And therefore, the time taken for that will be L of x, it is linear in L of x, right. And because we are taking expectation with respect to the hash function h, therefore, the expected query time for the element x is order 1 plus expectation over h L of x, right. And similarly for inserts and deletes, right? Because when you have to insert an element, you have to again look for the element, whether the element exists, and if it does not exist, then you insert that element. Similarly for delete. Okay. So, now this is the quantity that we need to analyze in order to bound the expected time for query. So, the core part of that quantity that you saw is this particular expectation, expectation over h L of x. So, how do we bound this? This seems like a daunting quantity. Let us try to create a bunch of very simple random variables first. For two elements x and y, x not equal to y, define the following indicator variable cxy. So, cxy equals 1 if h of x equal to h of y, that is h is telling you to map x and y into the same place, and c of xy equal to 0 else. So, therefore, now I can write down, now I can write h of x, now I can write L of x in terms of the simple random variables cxy. Okay. So, it is not hard to see that L of x is nothing but the summation over all y cxy, right, which is by the linearity of expectation. Now, I can propagate the expectation of h inside the summation, and because the cxy's are really 0 1 random variables, the expectation of cxy is nothing but the probability that h of x equal to h of y. And now, you see where the definition of universality comes in. Assuming that the hash function h that I started with is exactly universal, this probability is 1 by m for all pairs x and y, and because there is a sum over n values, the expectation that we get is n by m, right. So, this factor n by m, right, we intuitively call it the load factor of the hash table. So, in some sense you have to hit this factor in your query time, you can't do much better than this. So, next let us talk about how to create a universal hash family. Okay. We have analyzed, we have defined universal hashing, we have used it to analyze the query time, and but we still do not know that we can create a family of universal hash functions. Okay. So, here is a very simple method to do that. So, suppose you start with a universe u, look at the cardinality of the universe u, then choose a prime number p that is larger than this cardinality. Okay. Then define the following family, right. Look at all numbers a, small a, in the range from 1 to p minus 1, and for each such number there will be a function h a. So, what is this function h a? This function h a is nothing but this very simple operation. First you calculate, given a number x. So, we are thinking of numbers as, so we are thinking of element IDs as numbers in the range from 0 to cardinality of u. Without loss of generality, we can always do that, right. So, the function h of a is defined as, given any such input x, first you calculate the product a times x, then you take modulus of p. What does that give me? That gives me the remainder of a times x when divided by p. Okay. So, first you calculate a x mod p, and then you calculate the mod m of that, basically the remainder of that when divided by m. So, now what do we have? We have a number in the range from 0 to m minus 1, which is exactly what we desired, and we use this number as the value h a of x, which means that the place to store x in the array m. Okay. So, now it is pretty clear that choosing a hash function at randomly is basically the same as choosing a number a in the range from 1 to p minus 1 at random. Okay. And this is what we will analyze, that what happens when you create a hash function by choosing a number a from 1 to p minus 1 at random and calculating this value h a of x. Do we get a universal hash family? So, let us look at the quantity h of x equal to h of y. Okay. So, what we want to say that suppose h of x equals h of y. Okay. When can that happen? Remember, we get to choose a, we do not get to choose x and y are given to us. Okay. So in how many ways can we choose A such that h of A x equal to h A of y? So if that happens, right, then the A times x minus y mod p, right, must have been divisible by m, because this left hand side equals 0. Okay. Now A times x minus y mod p is a number from 0 to p minus 1. So how can that be divisible by mod m? How many such numbers are there that are divisible by mod m? It's not very hard to see. P is much bigger than m. So therefore there are exactly p minus 1 by m, p minus 1 divided by m values in the range 1 to p minus 1 that are divisible by m. Okay. So how do I choose A? In how many ways do I choose A so that I get to hit exactly one of these values? And here is where we have to look at some properties of prime numbers. That is, we are trying to analyze that what is the probability of choosing A such that A times x minus y mod p is one of these p minus 1 by m numbers. Okay. So without loss of generality, say that x is the bigger among x and y, and therefore x minus y ranges between 1 to p minus 1. In fact, it is smaller, but without loss of generality we can do that. So here is a very interesting property of prime numbers. Suppose you take any prime p, right, and look at two numbers t and z such that both t and z are in the range from 1 to p minus 1. In that case, what we can say is that there exists a unique number A in the range from 1 to p minus 1 such that A times z mod p equals t. Okay. So this reminds you of the property of division, right, in the case of let us say rational numbers, right. If I were taking if I had taken out this mod p, right, if I were sort of doing a normal division instead of doing a modulus, this property would have been obvious to you, but it is not so obvious because we are doing this modulus operation. However, it is easy to show why this is the case. That supposing this property is false, that means that suppose there are two numbers a and b such that az equal to bz mod p. In that case, what happens? In that case, what happens is that you get to say that a minus bz mod p equal to 0, because, and do convince yourself of this, that this modulus operation satisfies all these linear properties. But then a and b are both less than p, z is also less than p, and if the product of them is divisible by p, one of them must be divisible by p. But how can that happen? P is a prime number. So therefore, the product of them cannot be divisible by p, the product of them cannot have mod p equal to 0 unless a equal to b. So therefore, there exists a unique A that satisfies az mod p equal to t for all z and t in the range from 1 to p minus 1, right. What does this mean now? We were looking for the solution to a minus b times x, we were looking for the solution to a times x minus y mod p to be one of p minus 1 by m numbers. But what this statement means is that for each of these p minus 1 by m numbers, there is exactly a unique A, unique choice of A that is going to map x minus y to that particular number. So that means, and these are the only numbers that can cause collisions among x and y. So that means that the probability of choosing such an A is really only p. So there is only p minus 1 by m such choices of A that can cause a collision between two given x and y, and therefore the probability of choosing such an A is nothing but p minus 1 by m divided by 1 by p minus 1, which is equal to 1 by m, and that is exactly what we wanted, right, because that is really the definition of universal hashing. Okay. So next we will so while the definition of universal hashing of hash functions is very useful, we also need sometimes a little stronger definitions in some sense, right? And I won't show you how to construct such hash families, but it's actually fairly easy, right? So here is a definition of what is known as a k-wise universal, also sometimes called a strongly k-wise universal hash function. What does it say? What it says is that instead of taking x and y a pair, now we take a k tuple of values from the universe x1 to xk, and we take a k tuple of values from the hash positions 0 to m minus 1. So while the k tuple here x1 to xk are all distinct, the k tuple y1 to yk are not necessarily distinct. They can be few of them, I mean they can be the same, yi and yj can be the same. And what we want to say is that over the choice of the hash function, right, the probability that of this particular event, and this is an event over which is an AND over k possible simple events, the probability over h that h of x1 equals y1, h of x2 equals y2 and h of x equals yk equals 1 over m to the power k, right. If this happens, we call the function h to be a strongly k-wise universal hash function. So how do we create such a hash function? It's very simple actually. Rather than just using ax mod p, we now have to use a polynomial of size k, right. You have to choose I mean a1 to ak and therefore create a polynomial, and it's not very hard to say that by the uniqueness of roots of a polynomial you get this property. Okay. And in order to store this particular hash function, you will only need to store the coefficients that this polynomial uses, which is going to be of size k log n. There are going to be k numbers, each of them will only need order log n bits, and therefore it's enough to store order k log n bits. Okay. So just to summarize, we looked at the very basic data structure that we'll use over and over in this course, and that is a hash table. And we saw that a hash table really, there's no magic. There's a particular array M, right, where we store the elements, and if there is magic, it's all there in what is known as a hash function, and the design of the hash function is the most critical part of creating a hash table. So it's going to be a simple and versatile data structure, and the main issue is how to create this hash function. And just look up the Wikipedia page for that. There's an excellent literature about and it's a much researched area of how to create hash functions that are fast, that have provable properties and so on. What we also saw is that universality of a hash function, or even near universality, is something that guarantees small chain sizes and therefore guarantees faster query times. We have looked at only one particular method of handling collisions, that is known as chaining. That is, whenever we had a collision, we used a pointer, we used a linked list, right. There are other ways of handling chaining, which are and the most conspicuous one is known as open addressing. Okay. And this typically results in smaller smaller space usage, but it's much harder to analyze. Cuckoo hashing is a technique that's related to this, and that's a beautiful piece of work, but it's a little too advanced for our class. So that's it for today. Thank you for joining us for this lecture. The primary reference for this lecture is this lecture notes by Professor Jeff Erickson, Algorithms and Models of Computation. Please look up this textbook. It's an online resource at this point. There are other places where hashing and hash tables have been covered in quite a bit of details. The Standard Book of Algorithms by Common, Liserson and Rivest has a very nice chapter in it. The book on randomized algorithms by Mitzenmacher and Upfel also has a nice chapter on hashing and hash tables. So thank you.